Right, so I'll start. Yep. I'm Jarkko from the University of Helsinki. So I'm presenting our paper called Optimizing the Singular Value-Based Similarity Measures for Document Similarity Comparisons. And I co-authored this with Arto, Klami. So just an introduction. So usually the document similarities are quite often measured with some kind of simple measures using mean or maximum pooling. and this is followed usually then cosine similarity measurements. This is nowadays especially common approach, since we got these transformer models that are very flexible in their representational power. So usually this mean calculations are usually quite fast and powerful. So this results usually very fast computation when compared to the second order or matrix-based similarity measures. But the problem is that we lose quite much information, since we have to compress, especially in the case of full documents, we have to compress the words into a very dense representation that in long document case it can lose or compress quite much information into it. So we investigated the use of different matrix similarity measures using in this full-length document comparison task, and especially in the patent retrieval task. And we introduced these two new metrics motivated by the SHAT&P norms, which are these singular value-based norms, hence the name of the presentation. And we show that we can actually fine-tune these metrics to improve the results in this, at least in this full document patent search case. So just a quick kind of introduction what we mean when we say first order and second order metrics. So basically the idea is that when we're representing documents in the first order way, it means that we're basically using just some vectors which have only like point mass, and we compare the location of these points. Then when we extend to the second order, so-called matrix representations, we actually have much more mass, and the comparisons are a bit more robust in the sense that we also cover kind of directions where the variance exists. So the representation actually cover kind of an area instead of just points. And how do we form these representations? So we have some document, we represent each word just the word embedding, and then we just stack them together. And depending on which kind of representation we are interested in, we can either take some kind of pooling. So here, for example, mean pooling. So we get just a single vector, or if we do the covariance pooling, so we get the matrix format of the embedding dimensionality. So if we say that the matrix similarity measure is just a function that takes two objects A and B, where A and B are these document matrices encoded with these word embeddings. So when we have this similarity measure, when we want to create the similarity measure, we can use these norms as the basis for them. And we have this very general way. If we define that S is any submultiplicative norm, we have this very general way of defining any kind of measurements between matrices in a normalized way. And in normalizing, I mean that they are between -1 and 1. And this submultiplicative norm just means that it's a norm that satisfies this kind of inequality, which just means that basically we can always normalize whatever is on the denominator so that it will be between -1 and 1. And this is probably, if you're common with the cosine similarity, this is kind of exactly the same kind of trick that they do there. That if you have inner product space with vectors, you can then normalize it with the vector lengths, which is then the Euclidean norm. But here we don't define specific norm. We just need for it to fulfill this submultiplicative requirement. So the specific family that we built on is this called Schatten B norms. It's just defined as a singular values raised to the power of P, and then some of them are taken to then the Pth root. So this A is now the matrix that we're interested in, and so we calculate just all the singular values and sum them. And in addition to this, we consider this another type of metric where we have actually weights added to the standard Schatten B definition. So the idea here is that we can let the model learn different kind of weights for different singular values, as it has been shown that some singular values are usually more informative. For example, it has been shown that the first singular value usually catches this kind of a variance that exists only because of the most common forms. So basically stop words are usually the category that gives most information to the first singular value. So we might want to be able to remove this more flexibly than the P parameter lets us. So these V's are just weights, any real value weights, and the P has to be in the Schatten definition. The P has to be more than one, but also there is this quasi-norm definition for it where we allow the P value to be from 0 to infinite. And since we are interested in how well the singular values actually represent then these documents, we also look at directly this neural network approach where we give the singular values just as an input. So here we see that this notation means that the neural network just has the singular values of this matrix multiplication as the input. So it will be the input will be vector that is size of the embedding dimensionality, which is here D. And then we just run it through a few activation functions, and in the end we use the hyperbolic tangent just to make sure that we get the comparable similarity measure as from the previous, so it's between -1 and 1. From the experiment side, we had one full document experiment, so we evaluated this in the case of patent text. So the idea is that when patent examiners go through different kind of patent applications, they try to find kind of these objects for granting the patent, and these are usually called prior art. And then there are different kind of prior art. So usual two types are excitations and acitations. Excitations are so that if the patent examiner says that this is an excitation, it will be immediate reason to reject the patent. Acitations are then a bit less strong evidence against the patent, so it is similar to the patent application, but it's not enough for the immediate rejection. And this is important to be able to kind of differentiate between these categories, because then we can rank. If we have a search task, we can actually rank so that the X citations would be always before the A citations if we can somehow detect this automated. So then we can save a lot of work. So the patent examiner doesn't have to go through all the possible patents, but they can just focus on the most relevant, which are the X patents. So to learn this kind of differentiation between those, we use this, since this is essentially a ranking problem. So we take those previously mentioned covariance representations and input them into the triplet loss. We're using these similarity models that we defined previously. So S is now any of those similarity models mentioned before, or then in the case of the neural network, then it's just the neural network in replacement of the other similarity models. And here we use the traditional notation for the triplet loss. So A is the original document, so-called anchor document. P is the positive sample. So here it means that it's X because that is what we want to be closer to the anchor, and N is the A citation because that's kind of the negative sample that we want to push further away from the original sample. And here we have kind of like this diagram of how usually the system works. So we have a patent database that contains all the patents. We fetch all the data that we have. We have information for each patent. We have information about the descriptions and claims, and these are all linked to some kind of citations. So this is the training data case. And then in the search case, so the person who is doing the patent application, of course, he doesn't know what would be the X citation and what would be A citations. So the person wants to find all these relevant citations. So he knows that if he has to change the patent application in some way to not match these. And the goal here is, so without training, you probably would have a list of something like this, that where the X and A citations are kind of in random permutation, and we want them to be sorted in a way that X citations are on top and A citations are on bottom. So the training set we used contains 305,000 full-length patent applications, and we encode them using fast text embeddings, and then form those covariance matrices. So for each patent document, we get 300 times 300 times representation. And then we use these previously mentioned models, optimize them over using PyTorch library in a way that we have 2,000 samples as the training set and 500 samples always as the validation set. And the learning loss is the triplet loss. So after we run the training, we evaluate it with the leftover 1,000 triplets. And we know the task here is to measure if we can get the X citation to be closer than the A citation. So what we see here is that the mean does relatively well compared all these Schatten, these matrix representations, but we still get quite significant improvement. So here the index means the p-value for the Schatten metric, and so we can see that the Schatten always has some optimal value compared to the mean. But what is interesting that we can actually always have the best result with using these neural networks. So the neural network just has an input of pure singular values, doesn't have any other limitations. And the dataset is split into so the patents have two parts. So it's they have claims.
New line.
Sorry. Yeah. Okay. Yeah. The dataset is so split that the patents have the claims and description size, and in both cases the neural network is the best, and the Schatten optimal is then the second best. So what we can conclude from here, it seems like at least because of the neural network quite nicely that it seems that the singular values are enough to discriminate between full documents. And the second order metrics always seem to be better than the mean-based metrics, where we can always find the optimal region for the p in between 0.1 and 0.5. So in the sort of quasi-norm region of the Schatten p-norm. But however, always the neural network is the best approach. Yes, that was my last slide.